We're going to go over section 4.5, which is called Bayes' rule. This is pretty much conditional probability, but you need to do extra work in part A, part B. That's why this has a different name. The first thing you should do is a tree diagram. Here it tells you that 46% of the population is male. So automatically implies that 0.54 or 54 of the population has to be females. Then it says that if the person is male, there is an 82% chance that we have a computer, which means that there is an 18% chance that it will not have a computer. If the person is female, there is a 71% chance that it will have a computer, and therefore a 39% chance that it won't have a computer. So this is the first thing you have to worry about, that this is correct. So male, computer, male, not computer, female, computer, and female, not computer. The question is asking you what's the probability that the person doesn't have a computer. The only way to get to no computer means that it has to be male and doesn't have a computer, or female and doesn't have a computer. So all you have to do is multiply the probabilities. So the probability of no computer is 0.46 times 0.18 plus 0.54 times 0.29, and this is around 0.24. To find the probability that the person has no computer, that has a computer, you can do the same thing, or you can just do the complement. The complement that somebody has a computer is the probability that somebody doesn't have a computer. So this will be 1 minus 0.24, which is around 76%. Okay, now in part C, this is where you're going to need the conditional formula. The question is telling you that if a person owns a computer, what is the probability that the person is female? So this is female and computer. If we use the conditional probability formula, remember that this one goes down. Now you know this, and this you can get from the tree. So in our case, the probability somebody owns a computer is 76%. Now female and computer means this times this. So this is the same thing as 0.54 times 0.71, and this is around 50%, and that's it. And as you can see, the key to solving this problem is to have the correct tree diagram. Once you have completed this, you have complete A. To complete B, you can do the complement or go through the whole tree again, and you cannot answer part C without having completed part B or part A first. Okay, so let's do another example. In this problem, you have that a person either has a disease or they don't have it. If they have the disease, they take a test. The test is either positive or negative. The probability that somebody has a disease is 3%, which is this value. So therefore, the probability that somebody doesn't have the disease is 97%. He also says that if you have the disease, the CDC has a test that is 98% effective, which means it's a 98% chance here, and this should be 2%. If the person doesn't have the disease, the test should be negative. So this is 97, this is 0.03. Just like the previous problem, the question now is just asking what's the probability that the test will be positive? So positive will be this times this plus this times that. So it's 0.03 times 0.98 plus 0.97 times 0.03. If you compute it, it's around 0.06. Make sure you check that this works. Again, for part B, you can go again through the 3, or you can just do the complement, which is the easiest way to the problem. This is 1 minus 0.06, and this is around 0.94. Or you can go through this times that, and this times that. It will give you the same thing. Okay, now let's go to part C. Part C is a conditional probability. So it says, given that you know that the test is positive, so now you know the test was positive, what is the probability that the person actually has the disease? Using the conditional formula, this means disease and positive divided by positive. Now, positive from part B is 0.06, and that part A. It's part A, not part B, sorry. And on the top, disease and positive will be this. So that's 0.03 times 0.98, which again is around 50%. By the way, the answer is not always 50%. And that's it for section 4.5. Let's go now to section 4.4. This is a fundamental counting principle. We technically have done this before in section 4.1. Remember, in section 4.1, the first example we did, you have 3 kids. How many choices you have for each kid? 2, 2, and 2. And this is A. And remember, this was the sample space before. In the homework, you have a case where you have 2 dice, and you need to see how many choices you have. Remember, it's 6 times 6, which is 36. So what we want to do in this section is the same thing, just in a more formal way. So for example, how many social security numbers are possible? Assuming you can use all the digits, you have 10 choices for each of them. So therefore this is 10 to the 9, which is around 1 billion. So that means there is 1 billion different social security numbers. So therefore, if I give you a social security number like 222 12 12 12, and let's say, what would be the probability that this is Obama's social security number? And the probability of that this is Obama, it will be 1 over 1 billion. And that's it. You can do the same thing for IDs. Let's say that for IDs, case 1, you can only do numbers. So then it will be 10 to the 5th power, which is around 100,000. That's it. Case 2 is you can use capital letters and digits. And you can do this, then I have 36 choices. Why 36? It's 26 letters plus 10 numbers. Okay. So therefore, this is 36 to the 5th power, which is a pretty big number. So now, what will be the probability then that this AB123, that this is Pedro's ID number, and the probability that this is the ID number will be 1 over 36 to the 5th power. And that's that's it. You can leave the answer like this on the test. There's no need to simplify anymore. Okay, next example. In how many ways can 5 runners finish a race? Okay, let's say this is the first place, second, third, and so forth. You have 5 runners, so any of the 5 can be the first place. Then you have 4 for the second place, 3 for the third place, and so forth. So this is equals to 120. So I mean, that means there is 120 different ways to finish a race. There's a special notation for this, which you may have seen before. So this is called 5 factorial. As you can see, if I write 7 factorial, that means 7 times 6 times 5 times 4 times 3 is 2 times 1. For all of this to make sense, 1 factorial has to be 1, and 0 factorial also has to be 1. And that's it. Next, we're going to talk about permutations. So permutations means this: you have n objects to choose from, and you want to pick k at a time. If you do a permutation, the order is important. And by order, that means the picking order is important. So whatever you pick first will get something different than what that gets picked second, and so forth. So for example, let's say that you're going to pick 3 people. Whoever you pick first gets an A, second gets a B, and third one gets a C. So the order in which they are selected is important. So let's say you have 10 students in a class, and you're going to select 3 from there. This should be a permutation. So then this will be 10 factorial, and then 10 minus 3 is 7 factorial. Using the expansion we just did right now, this is 10, 9. So 4, 4, 3, 2, 1. This is 7, 6, 5, 4, 3, 2, 1. All of this cancel, and this is 720. By the way, the calculator can also find this, but you can just leave the answer in this form even. So for now, have 720. So what does this mean? That there is 720 ways to choose 3 people from 10 when the order is important. Now the combinations is very similar. The difference here is that the order is not important, which means everybody will get the same thing. For example, let's say you pick again 3 people, but whoever you pick, all of them will get an A. It doesn't matter who gets selected first. So if you do now 10 choose 3, so then this will be 10 factorial over 3 factorial times 7 factorial. We already computed this in here. This is 720. So this is 720 divided by 3 factorial. But remember, 3 factorial is the same as 3 times 2 times 1, which is 6. So this should be 720 over 6, which is 120. So notice how when the order doesn't matter, you have a lot less choices than when it does matter, which that's the way it should be. Now let's do a word problem related to this. So here you have a class where you have 4 Republicans, 6 Democrats, 3 Independents, and 7 Communists. So the total number of people you have is 17. You're picking a committee of 4 people, so for a committee the order doesn't matter, so you have to use combinations. The question is asking what's the probability you'll get 1 Republican, 1 Democrat, and 2 Independents. Remember, for any probability, you need to know the sample space. The sample space here will be 17. Choose 4. Why? Because that's all the different ways in which you can pick 4 people from 17. So this is the sample space. So throughout the problem, this is not going to change. Now, part it's asking that you want one Republican, one Democrat, and 2 independents. We have 4 Republicans, and we need 1. You have 6 Democrats, and you need 1. And you have 3 independents, and you need 2. You also have 4 communists, but you don't need any. So you should write this all the time. Anything choose 0 is equals to 1. So it will not affect if you don't write this, but sometimes if you forget this part, the problem is wrong. The reason why you should add this is that all the numbers on the left, 4, 6, 3, and 4, should add to this one, and all the numbers on the right should add to this one. Using the previous information, remember we're still selecting 4 people from 17. So what's the probability that you'll get 3 Republicans and 1 communist? Since we're still selecting 4 from 17, the bottom is not going to change. On the top, remember that you have 4 Republicans and you want 3. There is also 4 communists and you want 1. That means there is 9 people left and you don't need any. By the way, you can leave the answer exactly like this. There's no need to simplify anything. Just leave it like this on the test. Finally, what's the probability of getting 2 Democrats? Don't forget that we're still selecting 4 people from 17. So there is 6 Democrats and you want 2, but you still have to select 2 more people. So you have 11 left, which you don't care who they are, and you're going to pick 2. And in this case, if you forget this, the problem, it is wrong. Well, here or the previous one, you forget it, it's not. Okay? And that's it.